Hi, my name is Andreas Klingler. I'm a PhD student in theoretical physics at the University of Innsbruck, and I will present in this talk our recent work about approximate tensor decompositions, where we have shown that allowing for some approximation error in your tensor decomposition can lead to significant differences in the complexity describing a tensor. This is a joint work together with my PhD advisor, Gemma Cuevas, and also Tim Netzer, who is also located in Innsbruck and the leader of the algebra group. Now, tensors have this very special property that they can be represented as a sum of elementary tensors. And one important parameter in this setting is the so-called tensor-rank, which is the minimal number of elementary tensors necessary to represent a given tensor in such a way. And therefore, it can be understood as some measure of complexity represented a given tensor. Now, there is in fact not a unique way to define a tensor decomposition and its corresponding rank. There are in fact many different possibilities to do so. So let me introduce some variations. So, for example, one can introduce more than one summation index and arrange all the summation indices in various ways. In fact, one can do it according to any graph structure, where each vertex corresponds to a local space and each edge to a joint index. Now, going back to our initial example, graphs are not enough, as you see, but we can represent such a decomposition by a hypergraph. And so for this construction, you can choose any hypergraph you can think of and decompose a tensor according such a hypergraph. Another variation comes into play if we want to describe invariant tensors. So given a tensor which is invariant with respect to some particular permutations of the local spaces, this invariance is usually not reflected in the elementary tensors. So we can also define explicitly invariant decompositions, where each elementary tensor has to have the same symmetry like the global tensor. So, for example, if we have given a circular tensor decomposition, like in the bottom, then implementing translational invariance, for example, in the decomposition implies that all the local vectors have to be chosen independently of the local space. In recent years, more and more attention was also paid to tensor decompositions of positive elements. So elements contained in some specific positivity cone. I will give examples later on. Decomposing such elements in a naive way, like I've presented it up to now, the global positivity of all elements is usually not reflected in the local elements. So again here we have to introduce decomposition which have a local certificate of positivity. But in fact, such decompositions are in general much more costly than unconstrained ones. So in fact, we have studied in this work approximations of tensor decompositions including all those variations. But since our results have the greatest influence to inherently positive decompositions, so decompositions of the last type, we will focus in this talk most time on decompositions which have different local certificates of positivity. But first, let me motivate all these different types of decompositions by showing you two fields of applications. So, if we consider the tensor product space of column vectors, one notion of positivity would be given by so-called entry-wise non-negative tensors. And these tensors are very relevant in machine learning, especially in probabilistic modeling, since every non-negative tensor can be associated with a multipartite probability distribution. And different types of tensor decompositions can be interpreted in various ways using this correspondence. So for example, different arrangement of indices correspond to different correlation structures in a corresponding probabilistic model. different local certificates of positivity correspond to different types of probabilistic models. And knowing about the rank with respect to some corresponding decomposition can lead to insights about the expressive power of the corresponding model. I would also like to mention here that these positive tensor decompositions, in this case on this space here, are generalizations of different types of matrix factorization. So in particular, if we consider these tensor decompositions on a bipartite tensor product space, we would reobtain different notions of matrix factorizations, like the positive semi-definite factorization or the non-negative factorization. Another example where those tensor decompositions come into play are in the context of tensor network decompositions, which are very relevant in describing large quantum many-body systems efficiently. In fact, it has been shown that reflecting the physical geometry in the arrangement of indices leads to very efficient descriptions in many situations. So for example, matrix product states are a very efficient description of one-dimensional quantum systems. And in fact, there is also some notion of positivity in this context. So non-idealized quantum systems, so systems at finite temperature, for example, have to be described with positive semi-definite matrices. And so tensor decompositions of such elements can be seen somehow as quantum generalizations of the last slide, since considering only positive semi-definite matrices, which are in addition diagonal, we would reobtain the class of non-negative tensors. And therefore, I would like to focus on tensor decompositions of positive semi-definite matrices and their behavior in this talk. But please keep in mind that all the results I will tell you also apply to non-negative factorizations, so non-negative tensors, and in particular also matrix factorizations of non-negative matrices. So in the following, I will introduce tensor decompositions on matrices with different local certificates of positivity in the exact case first of all. And in particular, I will review the known results about their complexity. And afterwards, we will come to the approximate case of our work. Now, in the following, we will fix one particular geometry of arranging the indices, namely this circular arrangement of indices, and consider first of all no symmetries. And in the case of matrices, such an unconstrained decomposition is called matrix product density operator form, and its corresponding rank is called the operator Schmidt rank. What I would like to stress here again, that if we want to decompose a positive semi-definite matrix, then the local elements can be chosen in an arbitrary way, so they don't have to be positive semi-definite or in another subset of matrices. Now, one natural question is the following. Given such a decomposition of a positive semi-definite matrix, but without local constraints, is there any certificate of this global positivity in the local elements? Or do we have to spell out the whole decomposition and then check the global element about its positivity? And in fact, for such decompositions, it has been shown that there cannot exist such a local certificate, which is computable. This follows by the fact that given a translational invariant operator Schmidt decomposition, deciding positivity uniformly for all system sizes is in fact undecidable. But at least we can learn something else, namely, there is another cone of positivity which is also relevant for quantum physics, namely the cone of separable matrices. And by definition, separable matrices are those matrices which can be decomposed into a tensor decomposition where all its constituents are itself positive semi-definite. And so defining the corresponding rank over all such separable decompositions, we can define the so-called separable rank. Now, separable matrices are in fact a smaller cone than positive semi-definite matrices. So there exist positive semi-definite matrices which are not separable. So we still have no local positive decompositions for arbitrary positive semi-definite matrices. But this issue can be solved by introducing so-called local purification forms. So local purifications make use of the fact that positive semi-definite matrices attain a factorization of the form sigma dagger sigma, where the dagger is the Hermitian conjugate matrix. Now, local purifications are just matrix product operator decompositions of sigma, and so we can define the purification rank just as the operator Schmidt rank of sigma itself, where we of course have to optimize over all sigmas which attain such decomposition. Note that such decompositions are inherently positive, and hence we have given some local certificate of positivity. Now, as already mentioned at the beginning, we are in fact interested in the complexity of the ranks and the decompositions. So we want to know more about the corresponding ranks of the decompositions. And in fact, in some situations, one can construct one decomposition from a given other one. So for example, given a local purification form, one can construct a matrix product density operator form with some overhead by squaring the purification rank in worst case. So in other words, we can upper bound the operator Schmidt rank by the purification rank squared. But in fact, this is somehow not so interesting because a purification is much a stronger notion of decomposition as the operator Schmidt rank, since it contains some local certificate of positivity. It would be much more interesting to go the other way around and construct a purification from a given matrix product density operator form. But again, here we obtain a negative result, namely, this is impossible in general. In other words, there does not exist any function on the integers such that we can upper bound the purification rank by the operator Schmidt rank alone, and especially independent of the system dimension. So we obtain a very strong notion of separation here. Now, this behavior does not only appear between operator Schmidt rank and purification rank, it also appears between purification rank and separable rank, so also for separable matrices. So what we have seen up to now is somehow that we cannot decompose a given positive semi-definite matrix simultaneously in an efficient way and also with a local certificate of positivity in general. So in fact, this can be seen as a fundamental limitation in the complexity of representing positive semi-definite multipartite matrices. Now, as we have seen now, these separations and hence also these fundamental limitations appear in the exact case. But in fact, for many applications, the exact case is not the relevant case. The relevant case is the approximate case, where we allow for approximation errors in our decompositions. So the motivation of our work was now to ask whether these separations still appear if we allow for some approximation error in our decomposition. And studying this will be the next goal of this talk, where we show that in fact many separations disappear in the approximate case. So therefore, we first of all have to define what we mean by an approximate decomposition. So let us introduce them by directly defining the approximate rank. So for some fixed approximation error epsilon, we define the approximate operator Schmidt rank, for example, as the minimal operator Schmidt rank, which can be attained by some element in the epsilon ball of the original element. The used distance measure in our case here is the Schatten p-norm, which is for positive semi-definite matrices, for example, just the p-norm over all eigenvalues. And similarly, we can also define approximate versions of the separable decomposition and approximate purifications. Now, having these definitions, we are now able to state our main result. And for this reason, we distinguish two different cases. So first, we start by assuming that our matrix we want to approximate is not only positive semi-definite, but also separable. And what we have shown is, assuming that our matrix is a separable state, which means that it's not only separable, but it's also normalized with respect to the Schatten 1 norm, or equivalently the trace norm, then we can find an epsilon approximation whose separable rank is independent of the system dimension. And therefore, this especially implies that all the separations disappear for fixed approximation error. And the normalization condition is in fact meaningful for physical situations, for example, since quantum states are automatically normalized in such a way. So let us analyze this result a little bit more in detail. In fact, we have shown upper bounds for the approximate separable rank for a large class of values p strictly larger than 1, where the upper bound is just polynomial in the inverse error. So for a fixed error, this can be seen as a constant value, and this implies the disappearance of separations for normalized separable matrices. So the main technical tool in this proof was one version of the approximate Caradei-Rory theorem recently proven by Grigory Ivanov, where we have used that separable states can be seen as a convex hull of product states. In other words, a convex hull of elementary tensors where each local matrix is positive semi-definite and also normalized. Now, for general positive semi-definite matrices, we can show a very similar result using somehow the same methodology. But in fact, in this situation, the separable rank, of course, doesn't make any sense anymore. So we have to prove an upper bound of the purification rank. And so we have shown, again, for a large range of values p strictly larger than 1, that we can upper bound the purification rank for normalized positive semi-definite matrices. Here, as an example, an upper bound is given for p equal to 2. The main difference to separable matrices is that here we have to introduce an additional scaling factor, the so-called robustness of entanglement. And this value tells us how much we have to rescale our positive semi-definite matrix to write it as a difference of two separable states. So therefore, we can also imply here that the separations disappear in many situations, but here we have to assume in addition that the robustness of entanglement has to be bounded by some constant. Now, I've already mentioned at the beginning that we have studied approximate tensor decomposition not only concerning inherently positive decompositions. So let me elaborate in the last part of this talk how these results also apply to different arrangements of indices or including symmetries. So up to now we only considered the circular type decomposition. But in fact, all our upper bounds hold for general arrangement of indices. So in particular, we have introduced different tensor decompositions according to weighted simplicial complexes in a very recent paper. And here, for simplicity, we can also assume the structure to be just hypergraphs, as I have told you at the beginning. And in fact, we can prove the same upper bound, what I have already shown to you, for decompositions with just one single index, according to the simplex on the left-hand side. And every other arrangement of indices can be reconstructed starting from such a decomposition. And therefore, also the separations disappear for all arrangements of indices. Now, given a decomposition according to a simplicial complex, we can define also an invariant decomposition with respect to a symmetry group, which are permutations of the local spaces, or in the language of the complexes, permutations of the vertices. But in fact, to have a well-defined group action, the induced action on the multi-edges also have to be well-defined. And if this action on the multi-edges is a free group action, so it keeps no edge fixed when acting, when there is an action of a non-trivial element, then for every G-invariant matrix, we can also upper bound the G-invariant rank. So, for example, if we have given the circular decomposition, the group of translations is a free action on the edges, and hence we can upper bound the omega G rank by the rank itself, as long as we have given a G-invariant matrix. And therefore, also here, the separations disappear in the same situations as in the non-invariant case. So let me end this talk by some open questions and some outlook to further work. So we have seen that approximation results hold for a wide range of Schatten p-norms where p is strictly larger than 1. But unfortunately, our method breaks down if we want to get approximation results for p equal to 1, so for approximations with respect to the trace norm. But nonetheless, especially the trace norm is an operational meaningful measure in the context of quantum physics. So it would be very interesting to get an approximation result with respect to the trace norm. On the other hand, these approximation results hold in a very general setting, so including, for example, arbitrary arrangement of indices. So it would be definitely interesting to ask whether we can improve the results only including a subset of geometries, and perhaps find an approximation result also for the trace norm here. Now, we have discussed in particular two special situations, namely tensor decompositions on positive semi-definite matrices, including also separable matrices, and we have done this in detail, and also non-negative tensors, which has also been studied in our work with similar results. But in fact, there are also other very interesting examples of tensor product structures which have some additional structure of positivity. And one of them will be studied in an upcoming work where we study non-negative and sum of square polynomials in this context and show also there that separations appear in if we consider exact decompositions of such polynomials, and they disappear in the approximate case. With this, I would like to end this talk, and I would like to thank you for your attention, and if there are any questions or comments, I'm really looking forward to discuss them with you in the question session.